Thank you. Good morning, everyone. Thanks for the organizers for this wonderful meeting so far. And so I'm really excited to share some progress with you that we made by gathering these much larger samples of tidal disruption events. I think there were a few histograms already shown in this meeting, and in some cases the bars started touching 100 sources, right, if you combine X-ray and optical. So I think that is something to celebrate, and now we can see what we can actually learn with these large samples that we were all hoping for so long. And since this is a somewhat longer talk, I will also have a bit more leisurely introduction to help you wake up and tell you some things that you may already know. So let's start with some simple questions that you could ask, that you could discuss with someone right in an elevator, someone who's maybe not an astronomer per se. So you could wonder, are black holes spinning? And is any object that is gathering mass in an accretion disk, is this doing it in the same way? Maybe this question is already too difficult for an elevator talk, but but the third one I really like because it's very simple. Every galaxy hosts a supermassive black hole at its center. And since we're in a physics department, I think Brian said that they only occasionally allow astronomers in here. So we can also rephrase this into fundamental questions about physics. Right? So does the Kerr metric fully describe spinning black holes? And the second question now turns into the beautiful question about the scale invariance of accretion, which is basically saying, can I take any compact accreting object and scale everything just by the mass? And then there's a question about the occupation fraction, so does every galaxy host a black hole in its center? Turns out you can rephrase this about the black hole genesis in the early universe. So how did black holes form? So this last point I want to explain in a little bit more detail. So here is my PowerPoint cosmological simulation. So we have two different models for the origin of supermassive black holes. And the punchline is that we don't know how they formed. Right? So we have the model on the right, which is perhaps the most straightforward one, where you can get the seeds from the first stars that you form. They explode into supernova that you see there at very high redshift, right after the first galaxies form in their dark matter halos, which are those blue circles. And those first stars make tiny black holes of a few tens of solar mass or less, and then these accrete, and they give you massive black holes at the centers of every galaxy. Now, this is very difficult to grow these black holes, especially to the high masses we observe for high redshift quasars, and that leads to the second possibility. If you are able to suppress star formation in a subset of galaxies, then these don't fragment, and at some point their centers will collapse into black holes directly. This only happens for the highest mass galaxies, but then you start out with very massive black holes from this direct collapse scenario. And so it's not so hard to grow these into the high luminosity quasars we see at high redshift. But the consequence is, because this direct collapse can only happen for higher mass halos, that this model predicts we shouldn't see black holes in low mass galaxies. So we can discriminate these two models by looking for black holes in the lowest mass galaxies. So let's do that. And of course, we all know we can measure dynamical black hole masses if we can resolve the orbits of stars with spectra in the sphere of influence of the black hole, which is a few parsec, and that I'm showing here in this figure on the right. And if you do that, you can get these dynamical black hole measurements that you can see on the y-axis here. These correlate with the velocity dispersion of the host galaxy. This is the m sigma relation. But what about this bottom part here on the left? There we are really limited by angular resolution of our telescopes. So we simply cannot resolve the sphere of influence of the black hole. So we cannot do dynamical mass measurements of black holes at a scale that is only just below the black hole in the center of our own Milky Way, right? So this is of course the big problem. And there are a few low redshift galaxies that you can do this for, but we've basically tried it for all that are possible. So that brings us, of course, to this conference, and let's use tidal disruptions to solve this issue. Let's just measure the rate of tidal disruption events towards the lowest mass galaxies, then we can tell if these have black holes, and we can in turn learn how black holes formed in the early universe. Good, so then let's return to these fundamental or basic questions. So are black holes spinning? It turns out you can measure the TDE rate in high mass black holes, because due to the effect of the horizon directly capturing the stars, this is sensitive to the spin of the black hole. So if we measure the rate, we get a handle on spin. This question of scale invariance in accretion disk, we also heard this covered in Richard Sexton's talk. These state changes, if we measure these in radio and X-ray, then we can test this model. And finally, like I already said, this question about how the black holes formed, we can address by measuring the rate of TDEs in low mass galaxies. But none of this is easy, of course. So we need large samples to measure black hole spin. We also need to know how the luminosity of TDEs depends on several properties. And for this one in particular, we want to know how the luminosity depends on the mass of the star, because a higher mass star you can still disrupt in a higher mass black hole. So if you want to do spin measurements, you better understand how the luminosity depends on stellar mass. So that's the emission mechanism. And for this scale invariant model of accretion and using radio and X-ray observations, we really need to understand where the radio is coming from in the first place, like we heard in the first days already. And finally, this question about black hole genesis, we need everything. We need large samples, we need to understand the emission mechanism, and we need to know also the rate of TDEs as a function of mass. We need to have a prediction of this. And so I think looking at this slide on the right, you see emission mechanism appear 3 times. So let's focus on that for the rest of the talk. So let's see what can we learn about the emission mechanism in TDEs. And I'm focusing here just mainly on thermal TDEs, because that's what I've done most of my recent research on, and I think it's just for the sake of time. Let's do that. Okay, so first I have a statement that TDEs are real, and maybe this is not surprising to everyone here, but we have to remember that if we don't know the emission mechanism of TDEs, how do we even know that we are seeing them, right? That is kind of a problem already. Could they be something else? This has plagued the field for a while, and there are always people that are skeptical. But of course, we have now a mass function of TDEs from a uniform sample, the work from ZTF and summarized here beautifully in the paper by Yuan. And we see the effect of the black hole horizon in our data, which means that we are really seeing TDEs if we in the sample of optical sources we're looking at. There's one thing, yeah, I think that's what I wanted to say here. So let's look a little bit more detail, in a bit more detail at the optical UV emission. So here is real data from a real TDE that happened in 2010 and was found by Sufi Ghazari, and we have lots of follow-up data, and this is all summarized here as a function of blackbody luminosity. Okay, here I'm writing time since disruption, but this is still model dependent, but it doesn't matter. We have a rise time, we have a decay time, and a plateau. So these 3 things we can measure. Of course, we measure the peak luminosity, temperature. We measure spectral lines. And finally, there's also still substructure in this data that we can observe. So these are, I think, the key observables I want to summarize. So let's focus on the mini flares or repeating TDEs. I won't go into the repeating TDEs, but let's at least look at some structure in the light curve. We saw a great example of this yesterday by Yair, where we have a little bit of bumps in the pre-peak light curve, which is exciting because this early phase is probably the least understood. So if we see some variability, perhaps we can know what's going on. But I also wanted to point out, and I think this is not as well known maybe to all the theorists in the room, but we also see quite large bumps in the optical at late time. And in particular, this source is AT2019EHZ, and it has a pretty large late time bump. But still, I think even though this is surprising, I think what is more surprising is that these things are quite rare. So most TDEs have fairly smooth light curves, and that is perhaps surprising because even for a 10 to the 15 centimeter photosphere, which is sort of typical, the light travel time is only 10 hours. So if your streams are variable on longer time scales, we should see this as more variability in the optical light curves, whereas instead the optical light curves are pretty smooth compared to AGN, for example. Okay, so but this variability is still quite hard to constrain with your model. So I think let's look at another observed property. So what about the spectral lines? So we have a spectroscopic classification scheme, which is good if you are an observer, because you can take a spectrum of a source and you can classify it as a TDE, and you can even sub-classify it. So we have these three different classification directions that are based on the broad lines, and this was really pioneered by Yair in his first paper, that there is at least a continuum from helium to hydrogen sources depending on which lines you see, and I think this is useful. And we also have some understanding that these lines are really set by electron scattering. So it's not the same as in AGN, where it's the ionization and the virial velocity of the gas that sets the line width. But otherwise, we still have some open questions. And here I'm showing the black body radius versus the rate of tidal disruption events, and again colored with our sort of standard scheme for coloring these events. You have the hydrogen plus helium events. These are definitely the most common, both per unit volume and in flux-limited surveys. And they have smaller black body radii compared to the rest of the sample, and this is really statistically significant. So this is updated with the latest results here. And we also have featureless TDEs at the highest luminosities. They're really super rare and quite luminous and occur in high mass host galaxies. But first, if we want to understand why are these hydrogen plus helium TDEs the most common, perhaps this, at least what we see is that if they have small black body radii, they will have higher densities, and this can explain these lines, and in particular the Bowen lines that we see in these sources. But otherwise, I think this separation of the classes is not fully explained yet. And perhaps these are low mass stars because low mass stars are also more common. And I think we also got a question yesterday in this conference, so what about these featureless sources and their rate? So here is the rate of jetted TDEs. Of course, this is the volumetric rate, so you need to correct for beaming, which we don't really know how much the jetted TDEs are beamed. But if you have a beaming correction of a factor of 100, right, which is gamma squared, a Lorentz factor of 10, then the two rates do match. So this idea that featureless TDEs are related to jetted TDEs at least works in terms of numbers. Okay, so back to this figure again. Let's look in more detail at the different phases of the light curve. We have the rising phase, and I think there are just a lot of different possibilities here. Now we really get to the heart of the question, what is the emission mechanism? Right? Is it accretion plus reprocessing already for the peak? Did an accretion disk already form? Or is it the kinetic energy of the streams that is released and powers the rise time? Or is it a different kind of shock, this secondary shock from Clément's model? Of course, outflows are launched if you have if you can get a spherically symmetric reprocessing radius, but at the same time, the densities are still quite high in this early phase. So I think all of this, you also have to take into account the diffusion of the photons, and in some models, actually, the peak luminosity is set just by when these photons can escape. And then let's go to the decay phase. all of the same mechanisms that I just mentioned can still operate for the decay phase. Plus there can be a cooling envelope that we'll hear about in the next talk. So a lot of possibilities. So let's see if we can test this. We have the early time rise time measurements, and we have the decay time measurements, right? So you can plot them against each other, and you have a model that the rise time and the decay time have the same emission mechanism. If that's the case, then the rise time and the decay phase should be correlated, and indeed they appear to be correlated, so the null hypothesis that they're not correlated can be rejected. But throughout this talk, I'll be showing p-values here and there. But it's very important to know that even if the p-value is very low, it doesn't mean that you should completely apply this relation, because there is a lot of scatter, right? So when you have these large samples, all your p-values tend to be low, even if the relation itself doesn't look very good. In this case, I think the relation is fairly strong, but also with outliers. Okay, then let's keep looking at some correlations that are out there, because this is, of course, what you end up doing if you have population studies. And this one is nice because this was predicted a while ago in a review that we wrote. We have the black hole mass here measured from the m-sigma relation, and we have the fallback time, which is basically measuring a 5/3 power law decay and then getting this time scale of that power law decay. And this was already noticed by Thomas and also by Nadia back in 2017, that there is a correlation of this time scale post-peak and the black hole mass, and this relation really stood the test of time. So yesterday I remade this plot, and also you can see it in all those papers there, and the relation is still there, it's still significant. And there are other relations out there, like the peak luminosity and decay rate, which could also be correlated. Okay, so that concludes sort of the early time emission. So we have a correlation between peak luminosity or between rise and the decay rate itself seems to follow the fallback rate, right? So I didn't explain this, but the dotted line is how the fallback rate should scale with black hole mass in the simplest theory. We just heard yesterday that probably the effect of stellar structure, the stellar properties itself, cancel out. So that's great again in explaining this relation. Okay, then we get to the final phase, which is the plateaus. So we've seen a few plateaus, and the original, the classical approach is to find these with late time UV observations. So if you can get time on Hubble Space Telescope, you can observe these TDEs many years after their peak. So here you see in red and green, you see the optical data fading. We also have UV data all in the first year. It's all fading rapidly, and then suddenly there is still residual emission clearly detected in HST, or you can use Swift UV data for this assassin TDE, and you can see these plateaus very obviously by eye. But it's not always possible to get HST data, and also to get this much Swift data, the source has to be quite bright as well. Fortunately, we can also make a breakthrough with CTF forced photometry. And so here I'm showing optical light curves only, and this is the raw unbinned data. And if you squint by eye, you can already see that if you would bin this flux, there is still residual emission. So a single optical observation is not sensitive enough, but if you can combine them, which I'm showing in the top panel, you can clearly detect these late time plateaus using only optical, so that's great. And these plateaus are common. So if you do this for a large sample of some 60 TDEs, for which we have optical and UV data, then we have an 80% detection rate of the plateaus. So that's all the green stuff over here. And the red histogram shows if you apply this same methodology to just a random galaxy in the field, you don't accidentally detect plateaus due to issues in the difference imaging. So this is showing both that the result is robust and that there are many of these plateaus. And then we measure the luminosity of the plateau, and we compare it to all the other properties that we can measure, and we find the strongest correlation between plateau luminosity and decay and the mass of the host galaxy. So this is really significant correlation now, almost getting to 5 sigma, And here the scatter is also modest. It's 0.3 dec in the mass direction. And it turns out that these plateaus you can explain relatively well with a simple model for an accretion disk. So what does this model look like? So we have 6 free parameters. Of course, the mass of the black hole, the mass of the star, the inclination of the disk, or the cosinus of the inclination just tells you the area of the disk on the sky. There's black hole spin, impact parameter, and the viscous timescale with that curly V there. And I'm just showing here how the plateau luminosity, which is shown on the y-axis, scales with the black hole mass. And these color bars show you the dependence on some of these model parameters. You can see, for example, that the spin is all just noise or confetti for the low mass end, of course, because you're not sensitive to spin, except if you get to the highest mass, you need a high spin in order to disrupt the star. And so that's why that gets blue over there. And the dependence on inclination is also obvious, because as you get more face on, you will just get brighter plateaus, right? And the same is true for the stellar mass, because it's the mass in the disk. And finally, the impact parameter beta is not so important. So we have a lot of parameters, but as you can see from these scatter plots, you can also do a lot of simulations. You can make these predictions very fast. So you can marginalize over them, and then there is a fairly tight relation between plateau luminosity and black hole mass. So this is still a prediction, and the prediction is that you can turn your plateau luminosity into a black hole mass measurement. So of course, we then apply this prediction to the data, and we compare to the m-sigma relation, and then there is good agreement. So this is the velocity dispersion, and then the blue points show the black hole mass estimate, where now these, from the plateau luminosity, where the error bars take into account all the marginalize over all of those model parameters that we don't know. And then the gray points are dynamical black hole mass measurements from lower redshift. And you can see they continue throughout here a little bit. And so you can measure the slopes of both of these relations, and they're completely consistent. So that's nice. But then it turns out that this plateau luminosity is also correlated with the peak luminosity of the TDE. And the peak luminosity is much more easy to measure than these plateaus. You don't have to wait for 2 years to measure it. So then you can make an m-sigma relation using just the peak luminosity of the source. And that's shown here on the right. So that's the green point. Now the scatter is a lot larger, but there is still agreement. So this would be really, really neat, right? If you can just measure the peak luminosity and estimate the black hole mass, as long as you have large enough samples and you can average over this scatter, then you can really start to do science with TDE samples. Okay, so we try to take this one step further, and this is work by a student in Leiden, because I explained to you all the models of this late time accretion disk, and we can try to. We have a posterior distribution for all of these parameters, but only for a combination of them. So we combine them in a principal component. So this PC1 here is, you can just think of it as a combination of disk parameters. And so it's inclination, stellar mass, viscous time. And here is again the peak luminosity versus black hole mass, and the points are colored by the late time disk model parameters. But this is the peak. This is the early time. So if the early time knows about the late time, that would be really surprising. And if you squint, you can see that there is a trend here from going from this red color to this more blue color. And then we can actually write down a model to try and explain this, and then you can compare the likelihood of this model. So I'll flip back and forth, and this model. And there is a significant increase in the maximum likelihood if you include a combination of these late time disk parameters in your model for the peak luminosity. So that's quite surprising. So we're going to study that in more detail, because that would suggest a coupling. Okay, so then for the sort of last 5 minutes, I also wanted to compare these plateau measurements to other black hole measurements that are out there in the literature, because of course we're not the first ones to try to measure black hole mass. And so does it work? So there is the MOSFET package, which uses sort of the early time data and fits sort of a model that turns the fallback rate into a luminosity. And these two are correlated, but I think you agree that they're not consistent, right? So these are two different black hole mass estimates, and the dashed line would be a one-to-one relation. This we can rule out, even though they do agree to some level. We can also compare to the cooling envelope that we'll see next by Brian. Here we just have fewer data points, but they also are not correlated and also not consistent, obviously. So I made a few more of these plots, so let's go through them. This is now the velocity dispersion versus the TDE-based black hole mass estimate. And then there is some evidence for a correlation if you use the MOSFET-based black hole masses. And if you use, this is using the same number of sources, right? So we're always comparing the same number of TDEs. If you take those same TDEs and use their late time plateau to measure the mass, then you get slightly better agreement, but you can still see, yeah, there is still some scatter, but this correlation is somewhat more significant, but okay, fine. I think what's more interesting is to think about what if we take a step back and just do something again that is more simple. Just measure the fallback rate, right, which is again this t to the minus 5/3 decay, and compare it to the mass you get from the more complicated models. Then this is what you get. So the plateau-based masses are very strongly correlated with the fallback rate, and the MOSFET masses are not so, which is perhaps surprising because ultimately MOSFET is turning a fallback curve into a luminosity. And then finally, I think, and this is to motivate further discussion later this week, there are several papers out there that use MOSFET to measure the black hole mass, but they don't quite agree. And this is not showing that anybody is doing something wrong. And but I think what matters is which part of the light curve do you include? Because if you start seeing this plateau, then obviously a fallback-based model is not going to work anymore. So I think we can really clear this up in the next week when we're all here. Okay, so then this is my overview. Here at late times, when we have the plateau, we can definitely say it's powered by accretion. We saw this correlation of the fallback timescale in the post-peak data and the black hole mass, so that's suggesting that fallback is important there. There's also a correlation between pre-peak and post-peak, so maybe even the pre-peak is related to fallback rate, but I have 2 question marks there, so I think that is a lot more subtle. And then in the last minutes, I wanted to show some work in preparation. What can we do with these plateau mass measurements? Because they measure the mass of the black hole, so we actually can obtain a black hole mass function, or actually it's a TDE, it's a black hole mass function times the TDE rate, right? So we measure here the TDE rate as a function of plateau luminosity, and this you can fit with a simple parameterized model, which is just a power law with a turnover. And so it's not super surprising that we can fit this data with a simple model. But what is surprising is if you take this black hole mass function or TDE rate and apply it then to predict the X-rays at early time. Because if you say, I know that I have my black hole mass function, and I know that a plateau formed at late times, you can say if this is an accretion disk, what amount of X-rays does this accretion disk produce at early time? And then you can reproduce the X-ray luminosity function. So that's exciting. And of course, this break is again set by the effect of the Eddington limit. And then also, if you say that I have a linear relation between optical peak luminosity and black hole mass, you can also reproduce the optical luminosity function from ZTF only, right? Which is taking all the selection effects into account that could be there. So I think this is really fascinating that maybe with a very simple model, we can reproduce all the luminosity functions. So what's next? So we need to keep calm and find 1,000 TDEs with Ruben. So please reach out to me if you want to be involved with Ruben. I'm the coordinator of the TDE group, and we're really preparing for this rising tide. And here are my conclusions. So what observations do you need to explain if you're building models of tidal disruption events? We have quite smooth light curves. The lines from sources with the smallest back body radii are by far the most common. The rise and fade times are correlated, and the fade times themselves correlate with black hole mass, which is consistent what you would expect from fallback. And late time plateaus are common, so we certainly have an accretion disk at late times. But then at the same time, the properties of this accretion disk, like inclination or stellar mass, are also related to the early time data, so that's very exciting. And finally, if you have a linear scaling, we can explain all the luminosity functions. Thanks.
Okay, questions? Go ahead.
Hey, very nice talk. I love the summary. I was wondering, how confident are you that the ones for which you do not detect a plateau, there is no plateau? And does that correlate at all with the different types of TDEs? Like, is it the dimmest ones, which would be, I guess, the helium plus hydrogen ones, or is there any correlation there?
Yes. Yeah, thanks for the question. So I checked that the non-detections are not correlated with redshift or black hole mass or anything. So it's not. So I think it is mainly just sensitivity but that is throughout, that can happen at any redshift. There are some sources which really seems to be more consistent with a single power law, including so I think these plateau measurements are hard. So I think we're also limited by systematics. So it can be that the systematics make it harder to detect them. So I think we need to get HST observations for all of these before it's too late. So let's try that. Yeah. Thanks.
Hi, Sjoerd. I like the model that you have of, using the plateau to, make estimates of the black hole mass and doing the mass function stuff. Can you talk a little bit? I mean, it's kind of amazing how well it works for the X-ray luminosity function. So can you tell like a little bit more details on how you go from the accretion disk model, predict, like how do you do that conversion to the X-ray?
Yeah. So one thing I didn't say is that the normalization here, we're currently leaving it as a free parameter. But in principle, if you have this mass function, you can also predict this luminosity function. But then you would overpredict it because not every optical TDE is X-ray detected, right? So for now, it's only the shape, but the differences would tell you, for example, the importance of obscuration. So this is kind of an ultimate unification model where the X-rays themselves are not affected at all, right? So there's no absorption in here. So maybe that helps to answer your question.
Well, but even for getting the shape to match, I mean, do you have to make any assumptions about the evolution of the accretion disk?
No, not really. The only thing is that this late time model, you have the accretion rate is always sub-Eddington. So when we extrapolate, when we go back to predict the peak luminosity, we have to sort of, we need some scaling how the luminosity scales as you approach Eddington, because this disk model would break down. And that gives you this break, actually. So, and otherwise, it's just, if you remember that big scatter plot with all the colored points, it's literally just taking those posteriors, and for each one of those, you predict an X-ray luminosity, marginalizing over inclination and stellar mass, etc. And then that gives you this posterior. So this is the median, so this has some width after marginalizing over all of those properties. Yeah.
Thanks.
Take another question from here.
Yeah, hi, Sean. So the fact that you have such a good relationship between the peak optical luminosity, black hole mass, is this like a killer to say that it's obviously reprocessed disk radiation rather than shocks for the optical peak?
Yeah, I think, yeah, if you have any other model, then you have some degree of fine-tuning, perhaps, to explain this correlation. So, but if you have a model that makes the optical luminosity proportional with black hole mass, then you would always retrieve this correlation between plateau luminosity and peak luminosity. But I think the modest scatter in this relation, again, is very constraining, because it suggests that, yeah, if you have completely different physics to explain the luminosity at peak, then you would expect a lot less coherence, right, in that correlation. Yeah.
Go ahead.
Hello. So there's another code called TDE mass to calculate black hole masses for the shock model. Have you tried that out, or are you planning to do that?
Yeah, you mean the one that's called TDE mass, or?
Yeah. Well, any model that will give you, black hole masses based on the shock.
Yeah.
Shock model.
No, I didn't use that, but there are other, like, yeah, it's actually, it's a lot of work to turn all these LaTeX tables into, so I was doing that, like, in the past few weeks, so, but we can do it for sure. But one thing I will say, that this TDE mass-based model, it also doesn't correlate with MOSFET, or it also doesn't correlate with galaxy mass in the way that the plateaus do. So I'm not suspecting any surprises, but we should just do it. Yeah, thanks.
Sure.
So for the 6-parameter late-time plateau model, are you assuming like a thin disk that's subacting and accreting at this phase? Okay.
Yeah.
And to reproduce the early time optical luminosity function, is it saying that the fact that you match it so well, is it saying that the early time also comes from the disk part, the outer part of the disk?
Yeah, no, not necessarily. I think so. That's this plot. No, so the early times. I mean, certainly the early time optical is not coming from this disk. Like, that model doesn't work. So the only thing, what we're doing here to get this figure on the right is saying that if we take our black hole mass estimates from the plateau and we take the observed peak luminosities in the optical, there seems to be a linear correlation, and then you enforce that to the mass function that you already measured from the plateaus, and then you can reproduce your luminosity function. But why there is this linear scaling of optical peak with black hole mass, we don't know. But if you have a... Yeah, okay, there we go. So, yeah, of course, yeah, that's still, that doesn't mean that they're powered by peak. Yeah.
I see, thanks.
Yeah.
Yeah, I have a question about the featureless TDE rate. Somehow this agrees with the volumetric jetty TDE rate.
Yeah.
But the jetty TDEs, those host galaxies, the ones we have host galaxies,
Oh, yeah.
they don't seem to be the most massive.
Yeah, that's fair.
Host galaxies.
Yeah.
So do you think it's a coincidence that the rate can match, or do you think there's some deeper reason?
Yeah, if you put me on the spot, I think, yeah, I put this here because it came up as a question, and so I wanted to check. I think for now I would put it more as a coincidence than as actually meaning that they are the same. But that's my opinion. I think, yeah, that's all we can say for now.
And for those ones, let's say if we have this number, maybe like already 10 of them, are there really any jets in those? Have we actually looked? Those ones.
Yeah, that's not my work, but I think Yuan. Yeah, I think there is radio follow-up of these, so I think there are some hints that some of them will have. That some of them have radio emission, but I don't know if they're consistent with off-axis sources.
That would be really cool.
It would be cool. I agree.
Yeah, thanks.
Okay, thanks.
Go ahead.
Sure, really cool stuff. I'm curious about dust in your picture.
Yeah.
I guess the tightness of these correlations, right, between the plateau and even the peak and black hole mass, does that mean, do you think, that there are no partially obscured TDEs in your sample? And that there's really maybe this bimodal thing between heavily obscured TDEs and not obscured ones?
Yeah, I think that's fair. And where is the correlation? Maybe here. At least that if you have dust, of course, it would affect the plateau and the optical relatively similar, so that helps.
Yeah.
But I think if you have a lot of dust, then you would still severely underestimate this luminosity, and then that would wash out your comparison with the plateau mass. So yeah, there's a paper by Nathan Roth that looked into this, and it does seem like, that you quickly get this bimodal distribution. Like you either don't detect the TDEs because they're too faint, and then, so the ones we detect are relatively dust-free. Yeah.
Yeah, I'm interested in the plateau relation between plateau luminosity and radio flares at a late time. Some TDEs show very late time radio flare at 1,000 days after the optical discovery, and I speculate if something happened in the accretion disk at late time, maybe it can launch outflow.
Yes.
And did you find some hint, some variability to make it some outflow at late time?
Yeah, that's a good question. So far, like what Yvette said in her talk is also that this the source with the most extreme radio flare at late times is a very vanilla TDE, like very common. So there is nothing obvious. The only super speculative thing I can say is that if you look at that source, it's actually a power law all the way, so it doesn't have a plateau. So maybe it doesn't have a disk, and the whole disk went into this jet in a state change. That's my that's my speculative model, but there's nothing obvious.
Go ahead.
I had a similar question to Johan about correlations between the rise and decline. So you showed that there was a correlation between both of them, and then you also showed that the decline scaled, or there's a correlation with the fallback rate, which does to me imply that maybe on the rise there's more scatter, but it's somewhat scaling with the fallback rate as well on the rise. Is that kind of what you're thinking? I mean, there's multiple ways multiple sources that could do that. You could have stream collisions or potentially accretion do that, but is that kind of...
Yeah, that's kind of what I'm thinking. Okay. Yeah, but I put 2 question marks there. But the rise and decay are correlated, and the rise and decay time scale. So if the decay time scale correlates with fallback rate, then that could also suggest that that the rise is related to fallback rate. But I think these measurements, right, are quite subtle because the fallback rate is measured over a whole year. So you could still have something that sets your optical peak, and then and so I think it's this early time part. I think it can be different physics, but if it's completely different, then there would be no correlation. So that's how far I want to go.
And then I have one PSA about, like you said with MOSFET, it does rely on a single source of like luminosity following the fallback rate, so it absolutely will not fit well if there's a plateau, and that's, we can chat more this week, but that's definitely a known thing, but Yeah, so now that we know that these plateaus are there, we sort of know where to stop. That's what I recommend to anyone using it, but obviously that doesn't get to everyone.
Next.
Okay, final question from Elliot.
So one of the predictions of the spreading disk is that at longer wavelengths, one should see a relatively sharp cutoff in the spectrum because there's an outer edge to the disk. So is it possible to do near-infrared or other observations at the time of the plateau to try to really constrain the SED? Yeah, that's a great idea. I think it is, it's possible. These measurements in the optical are already challenging, and the only reason they're possible is because we have observations before the TDE with the same telescope in the same bands. So if you would do this in the infrared, you need really high quality reference frames because, of course, the host is even brighter in the infrared and the emission is fainter, so it gets twice as hard. But if you have, of course, if you maybe do this with James Webb, you get to high resolution. So yeah, it's a good idea. We should look into it. Thanks.
Okay, let's thank Sjoert once again.